Caching frequently accessed data is a technique to significantly improve the performance of your application, and in this video we are going to explore the most popular caching pattern. And this pattern is called the cache aside pattern. Another name for this pattern is lazy loading, and when I show you how this caching pattern works with a diagram, you will understand why it's called lazy loading. Here's a simple way to represent the cache aside pattern. We have three distinct components: a cache hit, returning the data from the cache, and a cache miss that causes us to fetch the data from the database but also write it to the cache. So fundamentally we have two paths inside of the cache aside pattern: the happy path, where the cache data is present in the cache and we can return it immediately to the application. But there is also the failure path, where we first have to check if the data is present in the cache. If that is not the case, then we have what's called a cache miss. This is going to cause us to fetch the data from the database or some other source where the data is coming from, and before returning it, we're going to write this data into the cache so that it's available for subsequent requests. Another commonly used pattern is the write-through pattern, which is often used together with the cache aside pattern. And here's how the write-through pattern works. When we are writing data from our application into the database, we're also going to update that same value inside of the cache, which means that the write-through approach ensures that we always have the cache data present in the cache. However, this also means that we might end up caching data inside of the cache that isn't so frequently accessed. So there is a trade-off to be made here, and in my opinion, the cache aside pattern is a more pragmatic approach. So now let's explore how we can implement the cache aside pattern in .NET. This is the application that I'm going to use for our cache aside pattern implementation. And it just has two API endpoints: a post endpoint that's going to insert a random user record into the database, and a get endpoint that's going to return a user with the specified identifier. This is a very bare bones implementation. The user record is defined here. I'm using Dapper to send the SQL queries to the database, and we have implemented a post and a get endpoint in just a few lines of code by opening a database connection with MPG SQL and executing a query on the database. So let me run the application and just show you how these two endpoints work. If I send a post request to the user's endpoint, this is going to create a resource inside of our database. So let's hit send, and we hit the breakpoint that I set inside of the endpoint. So I'm going to create a new Faker instance, open a database connection, and execute a query directly on the database that's going to insert a new user and return a response. Notice that we are returning a created @ response, which is going to be a 201 created HTTP status code, and is going to contain a location header pointing to the resource where the user is created. So let's hit continue, and we get a response back in Postman. But if I check out the headers of our response, you can see I have the location header present, and the response is 201 created as expected. But the important part is the location header contains the URI where we can fetch this user. So if I hit this URI, you can see that we hit the second breakpoint that I have, which is going to open another database connection, execute the query, and give me back the user. And you can see that we get back the user inside of Postman. So we want to introduce caching on the get endpoint to improve performance. Now inside of ASP.NET Core, we have two caching abstractions built in. We have the IMemoryCache, which is a service that allows you to store records inside of the cache using the memory of the server where the application is running. Another abstraction that we have is the IDistributedCache, which is thought of as an abstraction that can both work with an in-memory implementation, so much the same as the IMemoryCache. However, you can also connect it to an external cache such as Redis, or it can even use SQL Server. So because the IDistributedCache is more practical, I'm going to use that one to show you the implementation. Now the first thing I want to do is to move the code for fetching a user from the database into a local function. So let me extract this method, and I'm going to place it right here as a local function, and let's call this getUserAsync. I'm going to rename the variable here to user from DB so that it doesn't conflict with the variable that I will have inside of my minimal API endpoint. So let's close this down, and then let's see how we would implement the cache aside pattern. So the first step is to check if we have a value present in the cache, and to do that we need a cache key. So let's create a cache key, and let's for example say users and then specify the identifier value, and this is going to represent our cache key. Then I can say cache, and I have various methods available. The one I want to call is getStringAsync. We're going to pass it the value of our key. Of course, because this is asynchronous, we have to await it, and this is going to give us back the cached value. So because this is a string, we have to deserialize this into a user object. So let's call JSON serializer, deserialize, and pass in the cache value. The problem is that the cache value could be missing. So we only want to do this if the cache value is not null or empty, or let's say not null or whitespace. So in that case, let's add an if statement to check that. And I'm going to deserialize the cache value only if it's present. This is going to give me back a user instance. So because I have two users, I can go ahead and define them above. So let's say user, and this is just going to be my variable. And then we can use it to deserialize the value from the cache, or we're going to fetch it from the database and then set it in the cache. Now, because deserialization could fail, let's make this nullable. And after we have deserialized, if the user is not null, let's go ahead and return it. So I'll say return results okay, and then let's specify user. Otherwise, we want to fetch this value from the database, and then we want to set it in the cache. So I will say cache set string async, and then we have to specify our cache key and then the cached value. So I will say JSON serializer, serialize, and we will specify the user instance. And after this, we can go ahead and return this value from the cache. Before we can test out this implementation, we also need to register some services. So I will have to say builder services add distributed memory cache, and this is going to add an in-memory implementation for the IDistributedCache service. You could also introduce a Redis instance. Because I'm running Docker Compose, that would be very straightforward. And then you need to install the stackexchange.redis library, and you can connect the IDistributedCache with Redis. Now, I'm not going to be doing that because it's very simple. So let's go back to our cache aside implementation and let's see how it's going to work. If I go ahead and send a GET request to our API, we will hit the breakpoint on the GET endpoint, and we're first going to check if the value is present in the cache. Now you can see that the cached value is null, so this will be a cache miss. This is the failure path inside of our cache aside implementation. So in this case, we will head over to the database and try to fetch the user. You can see that the user is not null. What we could do is also introduce a null check after this step and only cache the value if it's not actually null. Otherwise, we would be caching nothing, and this isn't really valuable. So in this example, the fetch from the database succeeded, and we are going to set this value in the cache. And now I can return this from our API. The next time I send this request, we will again check if this value is present in the cache, and this time you can see that we get back the JSON string representing our user. So we are going to deserialize this into a user instance that we can return from our endpoint. Now the benefit here is that we are not reaching out to the database. Instead, we can satisfy this request from the cache, which is going to be much faster, and it also reduces the load on our database. I'll hit continue, and we get back the response in Postman. Another downside with the implementation that we have right now is that we would have to repeat this every time we want to introduce caching. So a better solution would be to introduce an extension method, which is available on the IMemoryCache implementation, but it isn't available on the IDistributedCache. So I'm going to introduce a static class that I will call cache aside, and let's make this a public static class. Inside of it, I'm going to define an extension method. It's going to be async, and it's going to return some generic value. I'm going to call this the get or create async method. It has to be generic, and it's going to be an extension method on the IDistributedCache interface. Now, what do we need from the arguments? Well, we need a cache key, and we also need some function that's going to, let's say, accept a cancellation token if we want to support this, and it's going to return a task which returns the generic value representing what we want to cache. So let's call this the factory function. Now, I'm also going to predict that we want to support cache expiration, so let's add an option to specify the distributed cache entry options. I'm going to make this a nullable argument so that you don't have to specify it. And let's also specify an optional cancellation token. Now, when it comes to the implementation, it's going to be very similar to what we already had. So we will say await cache get string async, and I need to specify my cache key, and I can also specify the cancellation token. And then if the cached value is not null or whitespace, then we can attempt to deserialize it, and it's going to be this generic argument. Of course, I can define it here so that I can reuse it later for my factory function. So let's say value JSON serializer, and I can say deserialize this value from my cached value string, and if the value is not null, then I'm going to return it. Otherwise, we run into a cache miss, and in this case, we want to invoke our factory function. So we're just going to call the factory method, pass it the cancellation token, and this is going to give us back the value that I want to assign to the value variable that I already had. So we have the value here. Now in this case, we also want to cache this value. So I will say cache set string async, specify the key, and serialize this using the JSON serializer. Let's pass in the value, and I can also specify the cancellation token, and finally I can return this value. Now you may want to also check if the value is null here, and if it is, let's just not cache it and let's return the default value. Now this also means that we have to predict that this method could return null to satisfy the function signature, and the only thing remaining is to use the cache options. So you can specify this when setting the cache value as an additional argument before passing in the cancellation token. So I'm going to specify the options if they are not null, otherwise I'm going to specify some default options. And this could be a private static read-only field. The type is going to be distributed cache entry options, and let's call this default. Now the value I can set here for the absolute expiration time relative to now could be 2 minutes. So every value that we cache and we don't specify an explicit expiration option, we're going to expire it in 2 minutes and is going to be removed from the cache. Now let me show you how we would use this from our minimal API endpoint. So the only thing that we will need is our cache key, and let's get rid of everything else. So let's leave the user in place. Let's remove all of the caching logic, and let's say that the user is going to come from calling our cache and the extension method that we have. So we will call get or create async. This is going to require the cache key, and we also need to specify a function that we are going to use to return the user. So let's say that the user is going to come from calling the get user async method, and we want to return this user from this function. I want to make it async so that I can await the execution inside. So we could also specify the distributed cache entry options by passing in a new instance if I want to manually set the expiration time, and I could also pass in the cancellation token. And it could be a good moment to update our minimal API endpoint, and if the user is null, then let's return a results not found response. And this is how we could implement a generic cache aside pattern. So let me quickly show you how this works before I discuss some of the drawbacks of this implementation. So let's send a request to fetch the user, and we hit the breakpoint in our minimal API endpoint. Now I'm going to press continue, and you will see that we land inside of the function that we are passing in to our extension method. So we encountered a cache miss, so we have to fetch the value from the database. So I'm going to hit continue, and we get back to response in Postman. Now I'm going to send this request again, and we again hit the breakpoint in the endpoint, but this time when I press continue, we immediately land back in Postman. So we fetch the value from the cache, and we can return it from the endpoint without having to reach out to the database. Now I mentioned that I wanted to discuss some of the drawbacks of this implementation, and if you take a look here, you will notice that we have a race condition. We could have multiple concurrent requests that execute the getString method, determine that they have a cache miss, and then proceed to fetch the value from the source by executing the factory function. This is what's called a Cache Stampede, and it might cause increased load on your database when many concurrent requests encounter a cache miss and proceed to fetch the value from the cache. Now, how you could solve this is by introducing locking. So let's implement a very straightforward solution. I'm going to create a private static read-only field that's going to be a semaphore slim, and I'm going to give it a name of semaphore, and let's give it an initial count of 1 and a maximum count of 1. So this means that only one thread is allowed to enter the semaphore. So what you would do is say semaphore wait async. You can even specify a timeout. So let's say you should wait for 100 milliseconds or however long you think a thread should wait before it says that it should fail. You will notice that this method returns a boolean which represents if the lock was acquired or not. So let's say has lock. Now if the current thread does not acquire a lock and the timeout has expired, you can go ahead and return a default value. Otherwise, you have successfully acquired a lock and you want to attempt to fetch the value from the cache. So the best way to do this is inside of a try finally statement, where we would move these parts here into the try step, where we execute the factory function and set the value in the cache, And finally, we're going to release the semaphore before completing this method. So we call the semaphore release method, making sure that subsequent requests are not blocked on this lock. So this implementation solves the problem of concurrent requests executing the factory function. However, we also need to check if the value wasn't populated in the cache before we were allowed to enter the critical section. So what we could do is execute this step here. So we would fetch the cached value again once we enter the try statement. So this would be like a double check with locking, and if the value is present in the cache, then we're going to return it. Otherwise, only then we are going to execute the factory function. So let me show you how all of this works. I'm going to send 2 concurrent requests from Postman to my API endpoint. So let's hit send, and then this is going to block on our breakpoint, and let's send another request for the same resource. You can see that we landed on the breakpoint on the get endpoint, and the first request is going to enter our critical section. So I will hit continue, and this request is going to fetch the value from the database and set it in the cache. And then this is the second request that's going to also enter the critical section after acquiring the lock, and I increase the timeout to 5 seconds. Now in this case, we will check if the value is present in the cache, and we will see that it is present. So we have a cache hit because another concurrent request already fetched the value from the database and set it inside of the cache. So after we have acquired the lock, we can go ahead and return the cached value. So I will hit continue, and you can see that both requests return the same response, but only one of them is going to fetch the value from the database instead of both. I want to highlight another drawback of this implementation, and that is that I'm going to lock on any cache key. Now this isn't ideal. What you really want to do is to be able to lock on a specific cache key so that you aren't reducing the concurrency of your entire application. So ideally, we want to cache by the key value, which means that only concurrent requests for one key are going to have to wait on the critical section. In general, I don't suggest that you implement this yourself. There are already libraries out there, like FusionCache, for example, that have built-in Cache Stampede protection, and we are also getting a new caching abstraction in .NET 9 that is called HybridCache and is going to support second-level caching. For example, it's going to have memory caching and distributed caching, as well as Cache Stampede protection. So this is something that was highly requested in .NET, and we are finally getting it in .NET 9. I'm going to make another video when .NET 9 is closer to release and HybridCache is more stable. This video wouldn't be complete without discussing the pros and cons of caching. So let's start with the benefits of caching. And the first benefit is that we have faster data retrieval. So reading a value from the cache is significantly faster than fetching that same value from the database because the cache operates in memory, which is a faster persistence mechanism. Caching also leads to fewer database queries because you will be able to satisfy most queries directly from the cache. You also get lower CPU usage because you don't have to compute as many values in your web application because you can just serve them from the cache. This also frees up your server to handle increased traffic, and when you introduce a distributed cache, you can apply all of this across a set of applications. However, there is no such thing as free lunch, and the same goes for caching, so let's discuss some of the drawbacks of caching. And the first drawback is increased complexity. When you introduce caching, you have 2 paths in your application for fetching the same data. One path is going to return the data from the cache, and the other one is going to return the data from the database or some other source. So this increases complexity, and you should be aware of it. Another drawback is that you introduce the risk of returning stale data. So let's say you set a value in the cache and it stays there for a few minutes. In the meantime, the source of truth, which is in the database, could change, and you would end up returning stale data from the cache unless you update the cache value. Caching also requires more storage in terms of server memory. This also applies if you are using a distributed cache like Redis. And lastly, cache data could be lost if your cache server goes down. The cache could be your application server or a distributed cache, and in case of Redis, you do have an option to configure a persistent cache, but by default, most caches operate in memory, which is volatile, and you could lose cache data if the cache server goes down. If you want to learn more about distributed caching with Redis, then you should watch this video next. Check out my clean architecture and modular monolith courses if you want to improve your skills, and until next time, stay awesome.